So let me start with the application of SN reactions. Applications of, one second, applications of SN reactions. All right. Okay. So first, you can see reaction of alcohols. Reaction of alcohols with, oh, what happened to my screen? Just a second. Start. Let's look at it. Let's understand what are the reactions of alcohols with HX. When I say HX, they are relatively concentrated. They are not aqueous solutions. Keep that in mind. Okay. Now, usually, whenever we write the rate, so rate of reaction for any SN, whether it is SN1 or SN2, it will be HI greater than HBr greater than HCl, and this is far greater than, which is far greater than HF. HF hardly makes any reactions on alcohols. Okay. Now, how does the reaction work? You see, alcohol plus HX. It could be any SN reaction. It could be SN1 or SN2, but it will give you RX and H2O. Okay, this is the overall reaction. Now, look into this example. If we have a tertiary alcohol like this, in case if you have tertiary alcohol and you are treating that with HI, you will get CH3, C, CH3, CH3 and I. Okay. The mechanism is simple. You know that when it comes to HI, HI will be in equilibrium with H plus and I minus. So there is sufficient proton concentration available in the solution. Therefore, if you take out this tertiary alcohol with proton, the lone pair will attack here. It gets protonated. This step is called as protonation. Protonation. This step is called protonation. So once you get protonation, the second step is to make sure that this protonated group will undergo dissociation. That is, water is coming out of it. Since water is coming, we call it as dehydration step. So the first step is protonation. The second step is dehydration step. Then you notice that the carbocation can undergo rearrangement, but in this case, the carbocation is already very stable. So then the I minus attacks on it and thus making it into I. So what is this one? This is nucleophilic substitution, because overall it has undergone substitution. Correct? So I hope you guys understood that first protonation step will happen, next dehydration step will happen, and then nucleophilic substitution would happen in this reaction. Okay. The same logic works even for even for what you say HBr, even for HCl. Okay. This will be the rate determining step where the formation of carbocation is observed. So remember, important note. Okay. Formation of carbocation is the rate determining step of the reaction. Okay. Clear on this part? This is the first important application, everybody. How the uh, halogenation happens on alcohol. Got it? Now, notice what is a preferred mechanism here. So, when it comes to mechanism, you can notice mechanism preference. Mechanism preference, if you notice. For example, if you take an alcohol and there are three types of alcohols we know. Okay. Three types of alcohols we have. One is 3 degree 1. Okay. The other one is 2 degree, put it. It is 3 degree alcohol. One is 3 degree alcohol, and second one is 2 degree alcohol, and then we have 1 degree alcohol. Got it? Now, if it is 3 degree alcohol, there is no question of it. It will always go via SN1 mechanism. Okay, it will always go via SN1 mechanism. Hmm. Hmm. Next, in case if we have 2 degree, check out. In case if we have 2 degree, how do we need to think? In case of 2 degree, it can go via SN1 mechanism as long as we are comparing this with HI, HBr, and HCl. In second degree, HI and HBr will definitely give SN1, but when it comes to HCl, there is slight difference there. Okay, and when we have 1 degree, it will always give you SN2 with HI, HBr, and HCl. Okay, clear. So this is the first important understanding we should have. Okay, so if you compare the rates now, comparing rates, all right. No just one night. Next, comparing rates. Check out comparing rates. So when it comes to 3 degree alcohol with HI, let's say this is happening with rate R1. Similarly, if you have 3 degree alcohol with HBr and it is happening at rate R2, so definitely rate of reaction of R1 will be greater than R2. So it depends upon, right? Correct. Important note is rate depends on strength of acid. Rate depends directly on strength of acid. So stronger the acid, easily it will break, and hence the rate will be higher. Okay, clear on that? Similarly, if I'm comparing again two rates here, please check this out. I'm comparing the same rates, but this time I'm taking a secondary alcohol here. If I take a secondary alcohol and I do HI addition only, in this case, definitely R1 is greater than R2. Here the note is, right, rate depends on stable carbocation, whichever will make stable carbocation. Correct? I'm sure you do understand what I'm trying to write there. Okay, clear? And whenever you are making an HI addition or HBr addition, you will always make carbocation. If it is starting from 3 degree or 2 degree, then you will keep on rearranging till it goes to the most stable carbocation. Once it reaches to the most stable carbocation, that's when you make the halogen to substitute. Okay, so yes, let's put into this into examples how it can be asked, right? So check out example one first. If you have OH here and then I'm treating with HI, so first we will get OH2 plus. It will convert into a carbocation. Now this carbocation will undergo, you know, rearrangement. Basically the bond will break here and attach so that it can become a three-membered ring with a carbocation, which we call it as CPM carbocation. And you know that CPM carbocation is highly stable. That's when I minus will attack, and final product which you will report is this one. This is major product that you will report. Okay, right? Check out example 2. If you have a tertiary alkyl group here and OH here, and then you are treating with HI, I'm sure you are aware of this factor that first you will get a carbocation. See, I'm slowly decreasing the number of steps. Okay. And then you will make 1,2 methyl shift. MS means methyl shift. In that case, methyl will shift here, positive charge will come here, and then iodide will get substituted on this position. So this is the product you will report. Correct? Example 3, if you have these kind of bicyclostructures and OH is here, okay, you notice that with HI here, first because it is being on the secondary position, it will make an SN1 reaction. So SN1 reaction, so which means first you will get a carbocation here like this, carbocation reaction here like this. Okay. Now, from this carbocation, you have to make a rearrangement to that carbocation form here. Correct. And notice the ring size, everybody. Correct. Here we have 1, 2, 3, 4, 5, 6 membered ring. But if I make this ring to go here, correct, the ring compression would happen. But as I break it, the positive charge will come here. So let me show how I am breaking it. This side I'll break, and from here I will connect. By which now I would get this as a 5 membered ring here, like this. 1 second. Methyl shift can happen here. Positive charge. No, no, sorry. Here there is one more methyl. I don't need that. Oh, we don't need to compress the ring. Sorry. Check out. Here we have a methyl. This methyl can shift onto this position here. Got it? With that positive charge here. So by which you will notice that a methyl will shift. So this is going to still be 6 membered ring. 1, 2, 3, 4, 5, 6. So I writing that as a 6 membered ring. Got it? And here where the junction is, between the junctions, if you notice, we have a group like this, and where the methyl got shifted, and we have a positive charge here. Still the positive charge will not come on that. Oh, oh. Sorry. My mistake. Hmm. Now we can't do that. Okay. Let me tell you the reason why. Because this is not the first carbon, it is on the second carbon. The rearrangement will always happen from the first carbon onwards. Got it? But this methyl I can't shift because at a bridge position it will be highly unstable form. Okay. So yeah, so in that case this is wrong. So here only I have to break it. I have to break it and connect these two. On connecting, what do I get here now? You'll get 1, 2, 3, 4, 5. A 5 membered ring like this way. And in here, if you put the numbering here, 1, 2, 3, 4, 5. And this is 1, 2, 3, 4, 5. Fifth and one got connected. And you see on the third position, because I have broken it, on third position here, this bond, this 1, 2, 3, because this one will be now on this position here, correct? And as it breaks here this time, you would notice that on third position we still have this group present here, and that is still connected to one. Okay, so 1, 2, 3, 4, 5. This is not broken. This is not broken. So we have one, right, and middle in the second one, and two, and then here. This is how it is present. And on this position, we have two methyl groups, and here we have one methyl group with a positive charge on it. Okay. So in short, we have like this. Let me rewrite that part. So we have a 5 membered ring like this. We have a 5 membered ring like this. In between, I have two groups here. Here there are two methyl groups. Here there is one methyl group with positive charge on it. And that is where the iodide will come and bind on it. So therefore, like this. Iodine will be here with methyl, and two other methyl groups will be here this way. All right. So this is example 3. Okay. So please go through it quickly. Check it out about the mechanism preferences and how the mechanism happens in these 3 cases. Quick. See, in case if you have like this double bond here, and then I'm making an HBr addition here. Got it? Here. In that case, check out. There are two products possible here, everybody. One product is Br coming at this position with a double bond here. Another product which you will get is uh, double bond shifting here and then Br coming at this position. Okay. This is called KCP product. That means kinetically controlled product. This is TCP, which is thermodynamically controlled product. Okay. Thermodynamically controlled product, you need to check out the more stable alkene. If you notice the alkene, there are 3, 2, and 1. Total 6 alpha hydrogens. Here we have only 2 alpha hydrogens. Okay. Here. Now, kinetically controlled relatively means you are operating at low temperature. Thermodynamically means you are relatively operating at high temperature. Okay. So now check it out. All right. How does the mechanism works here? Okay. First, we have OH, and this on protonation. This on protonation, OH will take proton to get this as OH2 plus. That OH2 plus will relieve to get a positive charge. This is most stable intermediate. First we get most stable intermediate. And from that, due to resonance, you can also get one more intermediate, which is getting this one. Okay. This is the other intermediate on which if at all you are reacting Br minus, then you will get double bond and bromine here. While if you put Br minus here, you can get Br here. So see, if you're directly getting a product from a more stable intermediate, then you call that as a KCP. Rather, if you're trying to get through an intermediate which is forming a more stable alkene, then you call it as a TCP. So this is a TCP kind, this is a KCP kind. Okay, clear? I guess this part is clear, everybody. Please check. Now it will be given to you that which one is operated. I mean, at low temperature. Chalo. Check it out. Here, close it up. So you could notice that in this case, if by chance high temperature is not mentioned or low temperature is not mentioned, if nothing is mentioned, you'll always give priority to TCP. So keep that in mind. See, because I have not given anything, I would write this as the minor product, okay, and this as the major product. Okay, so generally this will be the major product here. Clear? Let me put one more example of a similar kind. Okay, what if I have like this double bond O here and OH here, and then I'm treating with HBr? Again, it follows through, you know, SN1 mechanism. OH2 will be formed, this will be relieved, and a carbocation will be formed here. From that carbocation, due to resonance, double bond will shift here, positive charge will come here. If you are adding Br minus directly, then you will get a minor product. In that case, the minor product is KCP. This is minor. And in case if you are adding Br minus, then it is TCP, which is major. Clear? Please check these two cases quickly, everybody. I hope you guys understood this points. All good. See, next thing we need to understand, whenever we have alcohol which has a partial double bond character, okay, if you have OH here with double bonds like this, then what happens here is the lone pair is always in resonance with this ring. So therefore, you will have this resonance stabilization like this. Okay, because of which, okay, because of which, if at all you react with HI, you will not find any reaction happening. So remember, if there is any partial double bond character, no reaction. Another case, vinyl. If you have vinyl alcohol, correct? Here, there will not be any reaction with HI. In fact, it would always convert itself into aldehyde here, correct? And this aldehyde does not make any direct reaction with HI. Got it? So keep that in mind. So which means, suppose if at all I have an OH like this is a benzyl alcohol and this is a phenolic position. In that case, if you react with HI, even with excess also, then also that phenolic position OH will not be exchanged or removed. Instead, this side you will get iodide. Okay, so that you need to keep in mind. Clear? Second thing, in case if at all you're reacting this with, let's say, OH, and there is a methyl group here, and then you are treating with HBr, correct? In such cases, you will see you will have OH here that will not be replaced, but here Br will come. While Br is coming, it is, having a chirality. This chirality will always have plus and minus because it was a carbocation on which bromine is attaching. So hence you will get a racemic mixture. So in this case, we will get a racemic mixture. Clear, everyone? Okay. So this is an important area. I think you should be able to figure out how it is happening. Hmm. Right. Next, when it comes to substitution of alcohol by HCl, check out. Okay. Substitution of alcohols by HCl. If it comes to HCl here, see, normally, first thing you got to realize that ROH plus HCl concentrated, okay, makes very poor yield. You will get a poor yield of alkyl halide. Got it? Why is that so? That means alkyl chloride. Why is that so? Okay. Because I told you that the rate mainly depends upon the acidic strength, and HCl, although it is a strong acid, it has a very strong bond dissociation energy of HCl. So it is difficult to break that part. Okay. Hence, HCl is always used with, HCl is generally used with, not always. It is generally used with, okay, anhydrous, anhydrous zinc chloride, anhydrous zinc chloride, and which we call it as Lucas reagent. This is called as Lucas reagent. Got it? So here what will happen with the reaction is HCl plus ZnCl2 will react with each other to form ZnCl3 minus, and H plus will be released. So that's how the H plus will be more available. Okay. So this will, you know, ZnCl2 increases the H plus ion concentration. It will help in increasing the H plus ion concentration. Okay, clear? So therefore, if you notice any alcohol here, correct, and you are trying to make a reaction, you will see these reactions happening. First, if you have 3 degree, if you have 2 degree, if you have uh, 2 degree with two cases, I'll write two cases separately, and lastly with 1 degree. So if you have 3 degree alcohol, correct? Sorry, if you have, I already wrote this as alcohol, then typically SN1 reaction will happen with HCl, or generally HCl is more catalyzed with ZnCl2. Okay, when this will favor with SN1 if Cl minus concentration is high. If you have high concentration, otherwise it will be favoring SN2 if Cl minus concentration is low. Okay, if it is at low concentration. Oh, sorry, I wrote it ulta. This is SN2 and SN1. SN2 and SN1. Next, 1 degree generally always go for SN2, and this cannot be happening with HCl. It has to be done with HCl plus ZnCl2 only. So this will only give you correct reaction. Okay, I guess this part is clear, everybody. Please check what happens to the substitution via HCl quickly. What is relative rate towards SN2? What is the relative rate towards SN2? That is, suppose, imagine this is the reaction happening where a nucleophile is trying to attack CH3X, okay, in the presence of acetone, in the presence of acetone. In the presence of acetone. Then we are expecting this to become nucleophile with CH3 plus X minus. Acetone is the solvent here. Then the nucleophilic strength with respect to its relative rate. Okay. So we are comparing that with water or methanol. Water or methanol will typically have a similar rate. Okay. Let's say that will be 1. Then if you take F minus, F minus will act faster. It will be around 500 times greater than that of water. Then CH3CO minus, okay, 20,000 times. So CH3CO minus is a very good nucleophile for SN2 at methyl position. Okay, Cl minus, okay, you will see uh, 23,500 times greater. Ammonia, 3 into 10 raised to power of 5 times. Very good nucleophile. Okay. Phenoxide, PHO minus, 6 into 10 raised to power of 5. Got it? N3 minus, azide. Azide also 6 into 10 raised to power of 5. Very strong nucleophile. Okay. Br minus, 6 into 10 raised to power of 5. CH3O minus, alkoxide, 2 into 10 raised to power of 6. Okay. OH minus, excellent nucleophile, 3 into 10 raised to power of 6. Trimethylamine, okay, it will also be a good nucleophile, 5 into 10 raised to power of 6. Cyanide, 5 into 10 raised to power of 6. I minus, 25 into 10 raised to power of 6. And PET thrice, that is triethyl triethyl phosphor, 5 into 10 raised to power of 8. Very strong nucleophile. SH minus, 10 raised to power of 9. PHS minus, 7 into 10 raised to power of 9. And PHSE minus, so 5 into 10 raised to power of 10. So this is the increasing relative rate of nucleophiles. Got it? This is just to give you a data about how the nucleophiles are in general, how they are observed. So I put all of them here. PHSE minus will be stronger nucleophile than PHS minus, then SH minus, then PET thrice, then I minus, then cyanide, then R3N, then OH minus, then methoxide greater than Br minus, N3 minus, phenoxide, ammonia. Okay, this part you should know. Clear, everybody? Done? Right. Chalo. Next. Next. Check out. Check out. In case. Get your phone. Hmm. Second. Just give me a second. Now let's understand a special case which is known as SN2 prime and SN1 prime. How these two are different than SN2 and SN1. Okay. Correct. So these are occurred only in unsymmetrical uh, allyl halides. Unsymmetrical allyl halides. Okay. Correct. Now, how does it come here? Check out the example. Suppose in case if you have an symmetrical allyl, then a nucleophile, if it is attacking, it will usually attack at this position to get nucleophile. So we say it is simple SN2 mechanism. Okay. Or in fact, you will notice that if in case if you have it this way, the attack of nucleophile could actually happen here also. On double bond will shift, this group will shift. In that case, we are getting the same product, correct? But this mechanism type is called SN2 prime. So another important factor is, okay, attack on sp2 carbon. Now it is on sp2 carbon. So when the attack happens on sp2 carbon, that is SN2 prime. Okay. Now, of course, this is symmetrical kind, but the attack can be expressed as SN2 prime, but the product is same. Now see, when it comes to unsymmetrical allenes, allyl groups here, if a nucleophile is being shifted and you will get a nucleophile here, correct? We say this is via SN2 mechanism, okay? But in case if you have a bromine here, double bond here, and a nucleophile is attacking on this position, which is sp2, pushing the pi bond, relieving the bromine, in that case, we'll get double bond here and nucleophile here, Br minus will be out. Now, this is what we call it as SN2 prime. So, I hope you got an idea what is SN2 prime here. Okay. Generally, you know that attack of nucleophile will be more easier in sp2 compared to that of sp3. Therefore, in SN2 prime, I mean, if the reaction is given, you will report this as major and this as minor. So usually, usually SN2 prime is greater than SN2 when it comes to major quantity. Okay. Second. Second. Right. Next, let us understand what is SN1 prime. Okay. Now imagine if you're reacting this nucleophile, but it is going via SN1 reaction. So let me show with an example only. Suppose I have a double bond here like this with chlorine here and I'm reacting with H2O. You know that H2O is a weak nucleophile, so it will favor SN1 reaction. If it is via SN1, basically it means that we have a double bond, a carbocation is forming here, and without rearrangement also, if OH2, that means OH is coming at this position, we say it is via SN1 mechanism. This is via SN1 mechanism. Okay. But in case if you have chlorine here, instead water first carbocation is forming here the way it was supposed to form, and then due to resonance the double bond got shifted onto this position, positive charge came, and once the positive charge came and then water is attacking on it on this side, and we will get a product like this with OH. So this is called SN1 prime. Okay. Now, but this time, usually speaking, usually if you compare SN1 versus SN1 prime, SN1 will be major product. This will be major product. Clear? Reason being, when the carbocation is forming, the carbocation to shift here will be slightly difficult for the reason that if you have it like this, double bond and positive charge, okay, the halogen which is left here, X minus, will be in the close vicinity as it is leaving. So the positive charge will spend more time here as compared to that of spending time at this position. So this intermediate will be in larger quantity as compared to that of the second intermediate. Hence, this one will lead to the major product formation. So SN1 typically forms major product. So I hope you guys understood the difference between SN1 prime and SN2 prime. Yeah.
Sir,
हाँ तनिष, any doubt बेटा?
sir, yes, sir. If the
Hmm.
carbocation,
Notice the next set of reaction known as intramolecular 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 substitution, which we write it as SNI. Okay, clear? Usually, when non-polar or aprotic solvents are used, correct? SNI mechanism is observed. Is observed. Okay, here. And if basic solvent is used, basic solvent is used, SN2 is favorable. Instead of, that means it will compete with SN2, and this is what will happen. Okay, so check out. For example, if you take ROH plus SOCl2 in the presence of CCl4, which is non-polar, you will notice this will go via SN1 mechanism, and you'll get this as RCl plus SO2 plus HCl. Okay, basically SNI, with an example, if at all I have to show you, suppose I have a methyl, hydrogen, deuterium, and OH, and then I'm treating that with SOCl2 in the presence of either ether or CCl4. Got it? In that case, the major product will be, removing that OH and replacing the chlorine at the same position. Okay, so that means through SNI, what is happening, if this configuration is something like a dextro, then this will also remain dextro. That means if this is, let's say, R configured, this will remain R configured. So we say it is retention. Okay, R does not mean retention, so I'll just put it as S and S. Okay, just to avoid that confusion. So you will always notice a retention of configuration is observed. It is retention of configuration. But the minute we use it in a basic medium, okay, that is, if you use the same thing in a basic medium here, correct? So basic medium is, let's say we take pyridine here, like this. If we take pyridine instead of CCl4, then the mechanism go via SN2 here, and you'll get this as RCl, this, and pyridinium chloride. You'll get this as pyridinium plus and Cl minus, pyridinium chloride. Okay. Now here, in this case, the configuration will get inverted. So we will get chlorine here and H here. So we will see, if this is S configured, this will become R configured, and this is an inversion of configuration. Inversion of configuration. Okay. So by making this into, an SN2 mechanism, this is called as Darzin's reaction. This is called Darzin's reaction. Okay. All right. Let me show you how the mechanism takes place in this case. Check out. Okay. So for example, if you have something like OH here, right? Let's say this is hydrogen, deuterium, and methyl. And then you are treating with, this is thionyl chloride. With thionyl chloride in the presence of CCl4 here, the first thing what will happen here is, uh, OH, the oxygen will attack on sulfur, making it as SO minus, Cl and Cl group with a plus charge here. H, D, and methyl will be present. Okay, and then This C, as soon as this electron will be pushed back, the Cl will come out of it. Cl minus will take H plus. Okay. And then we will get H D methyl. So S, we will get this as double bond O and Cl. Correct? See? See. Next. Now, what would happen here is once you get this intermediate, this is the intermediate which we got. Got it? Now, see how is the movement of the electrons will take place. Okay. So, if you have this deuterium here, let me show you as if this carbon has an oxygen which is connected to sulfur, which has a double bond O and a Cl here. Correct? And that has a Cl there. Okay. So basically this bond will break here and trying to convert into a double bond. Bond will break here trying to convert into a double bond. So this Cl minus will break and Cl minus will try to attack from the same direction. Cl minus will attack from the same direction. So as the attack happens from the same direction here, correct, you will see the configuration gets retained. Cl will be here, H will be here, D will be here, methyl will be here, and it will form SO2. Okay. Now, why this would happen here? See, notice carbon here, it is making a sigma bond with oxygen, right? And chlorine here has an lone pair present like this. And here this is connected with sulfur this way with a bond. And here this oxygen is connected with a bond like this. Okay, this is the situation of orbitals. Now see this orbital, what will happen? As oxygen tries to depart from here, this oxygen is departing, correct? And it is trying to express into a pi bond with the sulfur here. So this has to, the bond has to open up. The chlorine has to depart from here. So chlorine is departing from here. This is chlorine. And chlorine's another orbital which has a lone pair. Chlorine has a lone pair here, correct? Which is open to attack there. So you can see slowly the distance between this orbital, sorry, the distance between this orbital and this orbital diminishes and they will start overlapping. So you will see now these two orbitals of chlorine will start overlapping and here the pi bonding will start forming. This is the pi bonding which is forming. This is the moment of bonding that will happen. So which means from where the oxygen is departing, on the same position you are able to get the uh, chloride. Okay. And that's how the retention is happening. Okay. Now you might ask, sir, what is the reason behind it? You know, why this is happening? See, one very important reason is bond dissociation energy of S double bond O, which is way stronger than C double bond O and C single bond O. So oxygen is trying to make a double bond O strongly with sulfur. Okay, that's the reason why it is trying to depart from carbon and encouraging chlorine to attack internally. Okay, but by chance, if you notice the second case, why it is becoming SN2, right? So check out why it is becoming SN2. Okay, so in the case of the second reaction, let me first write the second reaction here. Here. If you notice the second reaction here, first pyridine which you have here, correct, plus HCl will become pyridinium, that is plus, and Cl minus, pyridinium chloride. Okay, this will become pyridinium chloride. And when it becomes pyridinium chloride, the chloride is freely available. Chloride is freely available. So that's why when you actually had this compound with oxygen, sulfur, chlorine, this intermediate was forming, right? Okay, where we have H, D, and methyl here. So because chloride is freely available, now this chloride is the one which will make the back attack to push this group, and then Cl minus will go. That's the reason why the configuration got inverted in this case. Okay, so plus SO2 plus Cl minus. Okay, so that's how the basic group will help in creating that high nucleophilic chlorides, and that chloride will be attacking from the back, hence making an SN2 mechanism. Clear? Sorry, please go through it once quickly. Everybody, check what is SNI here. So check this out, everybody. Next thing we need to learn is about NGP, neighboring group participation. Okay, this is also called as an chimeric and chimeric assistance. Sorry. So we will learn this case by case. Case one, when you have pi electron participation, which means suppose, okay, if you have a benzene with CH2, CH2 and OTS is present here. Okay, and let's say this is carbon 14. And then a nucleophile like OH minus is trying to attack on it. Okay, then the product will be like this. We will have, instead of OTS, we can get OH minus here. Okay, or let's say I took iodide minus. Okay, it's a good nucleophile. So I minus I am adding. So I'll get I minus here, and I'll get one more product which is also having I on this position. Substitution has happened, but this time the carbon 14 is here. Okay, 18 December 2015, right? Okay, so this is carbon 14. Now, how come this one and this one, both of them are coming, and both of the chances of forming is 50-50 percentage? Both of them chances of forming is 50-50 percentage. So check out the mechanism here. Okay, so here after some time. So suppose OT is being a good leaving group when it is trying to leave. So what happens? This pi bond will try to support this carbon here. Okay, and how does it happen? Check it out. So we will have this as CH2, CH2, and here this is a bond which is forming by benzene here, like this. Okay, and this is carbon 14, and OTS has gone from there. We have double bond, and a plus charge. So the pi bond from here has connected, and this is the intermediate which we have got. This is the intermediate which we have got. Okay. So therefore, now when the iodide is trying to attack on it, so you would notice that it could attack on this position and this position equally. So when it attacks on here, it can break on this bond. When it attacks here, it can break on this bond and retain its aromaticity. And that's how chances of getting both these products increases. So we'll get pH, CH2, CH2I will come, where this is carbon 14, and pH CH2, CH2I will come where this is carbon 14. Okay, both will come 50-50 percentage. Okay, I hope this part is clear, everybody. Okay, that's how the participation happens. Now remember the positioning here from where the leaving group is. So this is 1, 2, and 3. So on third position, we should have a double bond character. Then the double bond will support. Okay, not on fourth. Fifth also it does, but more often 1, 3 NGP is more observed. So remember NGP is best observed in 1, 3 pi cloud support. Okay. Another example, if I put this as an example, check it out. Here we have a double bond here, and we have 1, 2, and iodide here. Okay, so this is 1, 2, 3. On third position, there is a double bond. And then I'm treating this with OH minus. So naturally, if this, by chance, if this is carbon 14, let's say. So same logic will occur here. So we will get double bond with OH here, with this being carbon 14, while double bond with OH here, with this being carbon 14. And chances of these two are 50-50 percentage here. Got it? So I guess the first case is clear, everybody, how the NGP happens. Okay. And see, when it is making an NGP, internally the pi bond is attacking like a nucleophile. And whenever there is an internal attack, always the rate happens faster. 1 second. So check it out. So let me write down that as a note here. So generally rate of SN will be more in the case of intra SN compared to that of inter SN, which means SN NGP will be generally greater than SN1 or SN2 types. So where there is a chance of SN1, where there is a chance of SN NGP, it will always happen faster compared to that of its counterpart where you have only SN1 or SN2 happening. Okay. And next, alternatively, for one N type of dehalogenation, okay, for instance, if you have like this, we have X here and X here, and let's say I'm using magnesium to do that. Magnesium will always come with 2 electrons. So 2 electrons, 1 electron will go here and 1 electron will go here. When it goes, you can see dot and dot forming, and that dot and dot will convert into this cyclobutane form plus MgX2. Okay. So this is how you can see internally the termination can take place to get this cyclobutane. Okay. Now, next, when it comes to second case here, where a lone pair is supporting, case 2. Case 2. Lone pair support from third position. For example, if you have a sulfur and then we have some halogen here, and that I'm treating with something like OH minus, correct? So check out this example clearly. So in that case, you will get sulfur back here with OH this way. Okay. But if this was carbon 14, I would definitely get another compound where you have this as carbon 14 also. And chances of both are 50-50 percentages. See the mechanism again. Sulfur has a lone pair present on it, because of which the lone pair will internally attack on it as a nucleophile and get into this intermediate where sulfur is connected this way with a plus charge. And that OH minus can be connected on this position or this position equally. And if this is carbon 14, that's how you can get those two products, which being 50-50 percentage. Okay. Let me show you another example here. Got it? In case if you have sulfur here like this with pH here and hydrogen here, and here I have chlorine, and this side I have, let's say, methyl. Okay. Now see this interesting factor here, because internal attack has to happen, correct? Internal attack has to happen. The lone pair on sulfur will attack from here and try to remove chlorine. But for that to happen, it is like an SN2 reaction only. Because if you notice that there is a simultaneous attack and simultaneous removal. So here also it is SN2, and the next step is also SN2 here. So one more time you are making SN2 reaction. So therefore, you will get SN2 two times. One internal SN2, that is when the lone pair attacks from here, chlorine is removed from there. So you will get this as, hydrogen would be present here, but sulfur would be here like this. Methyl is here, phenyl is here, plus charge is there. Now again, when the nucleophile, let's say OH minus is attacking, OH minus can relatively attack on this position also as well as this position also. On both positions we can get. Okay. On this both positions we can get. So what do I get here now? Okay. So in that case, suppose if OH minus comes here like this, okay, then H will come down, okay, SPH will be here and methyl will be here. This is one product, and another product will be when SPH, which was supposed to be on this position earlier, that will come back, and OH will be back to the same position where it belongs. Okay, so these two products are possible. Got it? Now, if you observe that carefully here, correct? In this case, now this product is different than this product, isn't it? Structurally, they are different products here, correct? But if you notice this one, so there are two different products you're getting, but you can see you will be able to get the same products also. You'll get the same products also in case if both the sides there is only hydrogen. Suppose if this is hydrogen only, there is no methyl here. This is hydrogen only. In that case, you will get same product. Here you will have hydrogen, and here also you will have hydrogen. Now notice this carefully. This structure and this structure are exactly same again, but they are like mirror images of each other. Please notice them. They are like mirror images of each other. Hence, this will be 50-50 percentage and forms a racemic mixture. Racemic mixture. Okay. As a short note, what you can learn is that SNNGP is like, okay, 2 times SN2. So that means first an inversion will happen, second an inversion will happen, and eventually it will end up getting retention product. So two times when NGP will happen, you will get a retention product. I mean, two times when inversion happens, it will get a retention product. So remember, retention is what you will expect whenever you have SN NGP. One more example, notice, this is a very standard example. Suppose I have C double bond O, O minus. I mean OH here. We start with that. And I'm treating this with Ag2O moist. And here I have a, you know, uh, here I have, um, what is it? Yeah, chlorine group here, let's say. We have a chlorine group here. Okay. So with moist Ag2O, I'm expecting that OH should come. So what you will get here is this OH with the same configuration with CO minus Ag plus here. Correct. This will become the major product. This will become the major product. Let me do the one thing. This is followed by hydrolysis also, so that I can get the final same product. So this will get OH. And this will be major product, while the other side where you have OH going inside like this with COOH, this will be minor product. Again, the reason is NGP. So check first, when you have a chloride here, correct? And you notice I can write this as C double bond O here and O minus here. So this O minus will attack here, remove this chlorine, and that's how you will get an NGP form. Okay, so this is with oxygen and C double bond O, and then OH moist Ag2O is OH minus. That OH minus will attack from the same direction from where the chlorine has gone. So that's how again OH comes onto the same position, and that O minus will go again, and this will become CO minus again. Correct? So this eventually on hydrolysis, we will get COOH and OH. So I hope you can understand that. You could see that the configuration is retained. How chlorine was, the same way the OH has come. This is called retention of configuration. Right? So please see these two examples clearly.